To really get a handle on modern physics with all its wild, mind-bending ideas, you've got to start at the beginning. Because no matter how out there the new stuff gets, it all grew out of these classical ideas that, for centuries, seem to have everything figured out. So let's grab our tools and dig into this foundational bedrock of reality.
All right, so here's our roadmap. We're going to start with the absolute basics, the ingredients of our universe. Then we'll look at the hidden rules that tell those ingredients how to behave. From there, we'll see how energy actually moves around. And then we'll meet the master chef himself, the guy who wrote the recipe for how it all fits together. And finally, we'll wrap up by seeing two fundamental forces of nature become one.
So first things first, what is everything made of? And what makes it all go? To answer that, we really need to get to grips with two core concepts, mass and energy. Okay, let's talk about mass. You can kind of think of it as just the amount of stuff in an object, but more precisely, it's a measure of inertia, which is basically an object's stubbornness. It's how much it fights you when you try to push it around. The more mass something has, the more oomph you need to get it moving, or to stop it once it is moving. Now, what's really interesting is that physicists actually think about mass in two different ways. You've got inertial mass, that's the stubbornness we just talked about, but then you have gravitational mass, which is what decides how strongly gravity yanks on an object. For the longest time, everyone just kind of assumed these two were the same thing, and it turns out they were right. But it wasn't until the early 1900s that experiments proved it, and get this, that little confirmation ended up being a massive clue that led to some truly mind-bending physics down the road. And then there's energy. Probably the best way to think about it is as the universe's currency. It's what you have to spend to get anything done, to make something move or change or heat up. And the number one absolute unbreakable rule of energy? It's conserved. You can't just make it out of thin air, and you can't destroy it. You can only change its form. This one single idea is no joke, one of the cornerstones of all of physics. And energy basically comes in two main flavors. You've got kinetic energy, which is the energy of motion, a giant tsunami or even the jiggling molecules in the air that we feel as heat. And then you have potential energy. That's stored energy, just waiting to be unleashed, like in a coiled up spring or a stretched out rubber band. It's the energy of what could be.
Okay, so we've got our ingredients, mass and energy. But what are the rules of the game? Well, that brings us to one of the most beautiful and profound ideas in all of physics, symmetry. You can think of it as the universe's hidden grammar.
So what kinds of symmetries are we talking about? Well, there's translational symmetry. That's just the fancy way of saying that the laws of physics work the same everywhere. An experiment you do in your kitchen will work the exact same way on the moon. Then you have something a bit weirder called internal symmetry. The best way to think about it is, imagine you have a bunch of red and blue balls that all weigh the same. If your experiment only cares about weight, you could swap a red one for a blue one and you'd get the exact same result. That's the core idea. And finally, there's this really cool one called spontaneous symmetry breaking, where a perfectly balanced system, like a pencil standing on its very tip, inevitably falls into one specific, less symmetrical state. Right, so we have our ingredients and the rules. Now let's see how things actually get moving. One of the main ways energy travels from point A to point B is through waves and vibrations. And this image shows the two basic kinds of waves perfectly. See the one on top? That's a transverse wave. Think about shaking a rope. The rope itself moves up and down, but the wave travels forward, away from you. Now look at the bottom one. That's a longitudinal wave, like a sound wave. See how the medium gets squished together and then stretched apart, all in the same direction that the wave is moving? So what happens when two waves run into each other? It's not like two cars crashing. It's actually something much cooler. They follow a rule called the principle of superposition. They just add together. If two peaks meet, you get a bigger peak. If a peak meets a valley, they can cancel each other out. It's a super simple rule, but it leads to some really complex and beautiful patterns. And one of those beautiful patterns is the standing wave. Just look at this. When waves interfere in just the right way, they can create these stable patterns that look like they're not even moving. You get these spots called nodes that are perfectly still, and other spots called antinodes that are vibrating like crazy. This is exactly what happens on a guitar string when you pluck it. It's what creates a musical note and all of its overtones. So we have mass, we have energy, symmetry, and waves, but for a long, long time, these were all seen as separate pieces of a puzzle. It took one incredible mind to pull it all together and basically write the recipe for the entire universe. And then,
Isaac Newton showed up, and everything changed.
I mean, in what has to be the most productive streak in the history of science, Newton just laid it all out. He gave us his 3 laws of motion. He figured out the law of universal gravity. He completely changed how we understand light. Oh, and, as if that wasn't enough, he co-invented a whole new kind of math, calculus, pretty much just so he could describe everything else.
And at the very heart of it all is this beautifully simple equation: force equals mass times acceleration. This is Newton's second law, and it's the master key. It connects an action, a force, with what happens because of it, a change in motion. It tells you exactly how much something will speed up when you push on it. It's profound. And it's part of a trio, right? The first law is basically inertia. Things like to keep doing whatever they're already doing unless something messes with them. And the third law is the action-reaction law. You push on a wall, and the wall pushes back on you with the exact same force. These 3 laws, together, became the foundation for the entire science of mechanics. But Newton's genius didn't stop there. His law of universal gravitation was just a breathtaking leap of imagination. He realized that the simple, everyday force that pulls an apple from a tree to the ground was the exact same force that was holding the moon in orbit around the Earth and the Earth around the sun. With one idea, he tied the heavens and the Earth together under a single universal rule. Okay, so by the 1800s, Newton's picture of a clockwork mechanical universe seemed almost finished. But there was one last big piece of the classical puzzle to solve: figuring out the invisible forces of electricity and magnetism. For the longest time, everyone thought electricity and magnetism were 2 totally separate things. But then experiments started showing these really deep connections. It turns out that a moving electric charge actually creates a magnetic field. And as this image shows, if you move a magnet near a wire, you can create an electric current. They were obviously 2 sides of the same coin. And the person who finally put it all together was the brilliant James Clerk Maxwell. He took every experiment, every observation about electricity and magnetism, and wove them into one single, incredibly elegant theory of the electromagnetic force. But when he did that, he found something amazing hidden in his own math. His equations predicted waves that traveled at the exact speed of light. It was an unbelievable moment. He hadn't just unified electricity and magnetism, he had discovered what light actually is. It's an electromagnetic wave. So by the turn of the 20th century, physicists were feeling pretty good about themselves. Newton had conquered motion and gravity. Maxwell had conquered light and electromagnetism. The job seemed pretty much done. The famous physicist Lord Kelvin even said there were just 2 dark clouds left on an otherwise perfectly clear sky. Just a couple of small, nagging problems to clean up. And that, right there, is the turning point. This beautiful, complete, classical picture of reality was about to be completely blown apart. Its very success had pushed physics to the absolute limit of what it could explain. So the question we have to leave on is, what were those 2 little dark clouds? And how on earth did looking into them end up unleashing the twin revolutions of relativity and quantum mechanics? Well, that's a story for another time. But the bedrock we've explored today, this is the essential foundation that all of modern physics had to be built on.